thank you. So welcome everyone to my presentation, which is called One Small Test for Man, One Giant Leap for Software Quality, Adopting Apollo's Testing Principles. So let me first introduce myself a little bit. So I'm François, as you heard a little bit earlier as well. I'm a senior full-stack software engineer working at Karakun, and you can find the ways you can reach me here on the slide if you're interested. And also I'm an active member of the Swiss Testing Board, and I'm also an active member of the ISTQB working group of advanced and expert level. And I'm also the author of the upcoming security test analyst syllabus. And you also see a QR code in the top right. If you're interested in the slides, you can scan it anytime. It will be on every slide, so you don't have to hurry. Just don't forget until the end that at some point, if you're interested, you scan it. So let's dive in. Maybe you heard me mention the document already a bit earlier. You can see it's quite old. You can see it's called What Made Apollo a Success. It was published by the NASA after the successful space mission of landing on the moon. And you can see it is from 1970. So it's already 54 years old. So when I'm talking you through this talk today, keep this in mind that how old this is, and think about how relevant the things still are today. Or, I'm trying to go through things that I found in the document that I found interesting in relation to testing or software development in general that still apply today, or maybe are a bit different than we do things today. So we can discuss those things. And just out of curiosity, I was searching for the word test, and you can see there were 271 matches in general that it found, which I thought was quite a lot if you consider that it's 86 pages long. So there are over 3 words per average per page that are, using the word test. And if we compare that, for example, to the word develop or development, and you can see it only appears 81 times, so around once per page on average. So kind of if we just look at it from this perspective, just statistically speaking, it kind of means that testing played a very big role in, the Apollo space mission, as we can see here. So let's start out with the table of contents first. So you can always see the page numbers in the parentheses in case you're interested in checking it out yourself. And those are the page numbers in the PDF, by the way, and not the page numbers that you can see in the document itself. So you can see here already, it starts in the table of contents. We already have a big major chapter, which is called Testing to Ensure Mission Success. And kind of, I feel like this is a very fitting title, because isn't it also that we want to have our mission to be successful, our mission of delivering good software with a good quality, of course? I would say definitely yes. And I feel like this is definitely still true today, even just things that appear in the table of contents here. And if we go on, this is if we go to the introduction. You can see here that it already mentions 4 aspects of spacecraft development stand out: design, test, control of changes, and interpretation of discrepancies. And you can see that test is quite a big part of it, and it's mentioned in 2nd place. What I found to be even more interesting is that actually, if we look at test, it is already considered to be part of spacecraft development. So if we think about how it is today, it's starting to become more and more the norm that testing becomes the part of the development, but still sometimes it's considered to be kind of separate. So they were kind of ahead of the times if you look at that this way. And if you look at interpretation of discrepancies, this is kind of something in the veins of root cause analysis that we also do today. And I really found it interesting to see that they already were thinking about that in that depth. And then let's have a look here. So one thing they mention here is build it simple and then double up on many components or systems so that if one fails, the other will take over. And people of you that worked in high availability systems feel like this is familiar to them probably, because this is something that you also do today. If you have a highly available system, you at least double up, maybe even have 3 or 4 times the components depending on how critical it is. And you also have a failover, which is mentioned in exactly the same way as the words that we use today, which I also found very interesting considering this is 54 years old. But this is also more relevant than ever, with now Kubernetes being a very standard way of deploying applications, where it's very easy to perform rolling upgrades and have multiple nodes that are running at the same time, and multiple replicas of the different applications that we are running. And then you can see here they mentioned that the concept of in-flight maintenance was discarded as being impractical for flights. If we look at the modern day equivalent, or let's say the software development equivalent, in-flight maintenance in our case is kind of something like performing a hotfix. Because they mentioned that later that more telemetry was added and full advantage was taken of the ground's ability to assess system performance, predict trends, and compare data with pre-flight test experience. That's what we also kind of do today when we are doing monitoring and production. We also do the same kind of things here, and so this is also more relevant than ever. And this proved to be already a good idea back then, and it's even a better idea today, I would say personally. And if we look at a part in the introduction where it says Apollo test activities as the subtitle, they say that the single most important factor leading to the high degree of reliability of the spacecraft was the tremendous depth and breadth of the test activity. So we see not only maybe statistically, but also as they state here, the testing was a very big part of the success of the mission. And I would say that this still holds true today. Even testing is often a very important, if not the most important factor, as they mentioned here, for the reliability of the system. And of course, the better the depth and breadth is, the better the testing will be and the better the reliability will be. So this also still holds true today. What I kind of found interesting was that they also documented in quite a lot of detail how much time and how many tests they performed. And this is just, one table that I pulled out of it. And you can see on the right that they mentioned on the one hand how many tests they did, but also sometimes they mentioned the hours or the minutes that they spent doing those things. I found it quite impressive that they took the time to write that down and to look at those numbers in detail, and that they found it interesting to, really put an effort behind writing those numbers down and keeping track of them. And you can see that it's quite a lot. So if we just add up the hours and minutes that we can see on the right, not considering the tests that are mentioned without any time here in this table, then we get an equal of 4,104 hours. So if we, let's say, consider 8 hours per day of a workday, then this is an equivalent of 513 workdays. And this is around 2.33 years for one person, if we consider a year with 220 workdays. So you can see they spent really quite a lot of time. Especially later, you will see the plan that they had. I mean, I don't know how close they stuck to the plan, but if they really stuck to the plan, you will see that this is even more impressive that they spent so much time in that. And they mentioned also, most important of all, the tests gave them a tremendous amount of time and experience on the spacecraft and their systems. I feel like that's a point that's not really talked about a lot nowadays. When we are testing a system, this not only gives us the advantage that we are able to reduce the likelihood of defects, for example, but also this allows us to get more familiar with the system and get more experience with it. And maybe this helps us too to get to have some other advantages from this. As they mention, that experience, together with a detailed analysis of all previous failures, discrepancies, and so on, led us to the conclusion that we were ready to fly a lunar orbit with Apollo 8 and ready to make a lunar landing with Apollo 11. And kind of this is still holds true today in a way that when we spend time testing systems, This also gives us an indication of if we are ready to not fly in this case, but deploy the application in production or not. This gives us kind of the confidence that we need to be able to say, can we go live with the system or not? And they also mention here acceptance testing played an equally important role. I was not aware that acceptance testing was a term that was already that old, or that it was known from such a long time. And it really actually means the same thing as we understand today. And they say this testing starts with piece parts. So if we look at this from a perspective of a software today, then usually you could compare this to a unit test. So they already kind of started doing this back then. And then they mention each component or black box is tested before it is delivered and again before it is installed. So you can see they also did then, some more tests to ensure that, for example, when they, when they delivered it somewhere, to ensure that it wasn't damaged in a way. This still applies maybe to hardware nowadays, but I have to say I don't have enough experience with testing hardware, in an enterprise scale to be able to say if this is still something that is being done today. But I definitely would say that it makes sense to do this. I mean, for example, if you have an ATM where you have software on it and you ship it somewhere, it could be that something is damaged and then maybe the ATM doesn't work properly anymore. So definitely it doesn't only make sense to do testing before you ship out the ATM, but also after installed the ATM as well. And you can also compare this in software engineering, just with, for example, having checksums to check if when a software is provided and the software was downloaded, there was no corruption in transit, which obviously also makes a lot of sense. And this could be something that you could translate to. Then they mention that factory testing of the complete spacecraft begins. And this kind of is an equivalent of the system tests that we do nowadays, I would say. They mention here that individual subsystems are tested as installed, and then they test groups of systems together. So this is kind of a combination between a system test and also maybe an integration test where they test different groups of components together in individual groups, as they mention here, which obviously also makes a lot of sense today and still holds true. And then they mention the complete spacecraft with all of its systems functioning is run in an integrated test. I think here, even though it sounds similar to integration test, this is more of a system test. But I mean, technically, you can consider it to be an integration test as well, just with quite a lot of parts built together. And what I also found quite interesting is that they mentioned that they tested all normal, emergency, and redundant modes. So this meant that they even back then considered test coverage, maybe even though they didn't call it that, but they really paid attention to test all of the things in different modes because the things could be different in those. I mean, I'm pretty sure that some suppliers back then would not test all of those again, because there are for sure some redundancies or only maybe some differences are tested, but they really were very rigorous here, which I also applaud and I think makes a lot of sense even in today's standards. Then they mentioned that an important facet of acceptance testing is environmental acceptance testing. So this is not really the same as the test environments that we have today or that we think about as a concept today. But I think it kind of translates well. If we continue reading, it says the primary purpose of acceptance vibration testing and acceptance thermal testing is to find workmanship errors. Those two testing things they mention here, they are both considered to be part of environmental acceptance testing, at least in terms of this document here. And the purpose to find workmanship errors is still something that applies today. When we are testing, we are trying to find mistakes that happen, for example, in programming as well, which can very quickly happen accidentally, of course. And here it also mentions the environment has to be severe enough to find the fault. And I think that is a point where we see the translation of the test environments that we have today to the environments that they mentioned here. It's also important when you have test environments that you pay attention to do them in a way that you will be able to find certain defects. And they also recognized this already back then. Of course, here I mentioned, for example, a cold solder joint, which doesn't really apply to us, but more if you have a hardware that you deliver, then of course this could be something that is still relevant at this point. And also you can see they mention each component type, and I love how they say, of course, as if it would be something that is totally normal, had to pass qualification tests under even more severe environments. So they were not only content with just testing it under an environment that was severe enough to find a fault, but they went above and beyond and picked a more severe environment than what they expected to be in, which of course also makes a lot of sense. Especially they didn't know as much about space back then as we know now, and they were not able to be predicting totally if everything would be the way that they would guess it would be. And then they mention that nevertheless, our environmental acceptance tests sometimes uncovered design faults as opposed to workmanship faults that had been missed in the qualification tests. And this is also something that holds true today, that sometimes when we run the tests that we do, especially acceptance tests, we tend to notice some design faults that happened as opposed to only workmanship faults. And sometimes, for example, the requirements were wrong or they missed something in the requirements that was critical, and it only appears once you do acceptance tests. So this kind of shows also why testing is important in a different way. And it can find some things that are missed in other tests, like here they mentioned in the qualification tests. And they say that the reason was that a single qualification test may have missed a marginal condition which the large number of acceptance tests could catch. And also here it comes down to the coverage once again. So here they mention, that, for example, there may be single tests that may miss a certain marginal condition, what they call here, but this is more like let's say, a boundary value that they missed, for example, that an acceptance test would catch, for example. And then they mention, in terms of the flight missions, that they say that it evolved through an iterative and flexible process that was changed as time went on to take the best advantage of knowledge about mission operations and hardware availability at any given time. And I was kind of mind blown when I read this. They kind of were already working agile 54 years ago, which was crazy to me. But it's interesting and cool to see that this was so successful to them and that they thought that this was very beneficial. And they mentioned here the advantages that we have with Agile even today, where you would take best advantage of the knowledge that you have about the, not the mission operations, but the general operations that you have. And hardware availability is not really a issue for us nowadays, I would say. But still, if there are some shortages and you're developing hardware, of course, this could apply. And then they say that they use this to gain the maximum new experience, and also, which also, of course, is similar to the way that we work in sprints today, where we try to achieve a maximum of new experience each sprint, and then use this learning to improve. And here, what I also found interesting was they mentioned, without stretching either the equipment or the people behind their ability to absorb the next step. I feel like that's also something that's a bit underlooked today, where there's not much attention being paid to people not stretching themselves beyond their ability to absorb the next step. Today, at least in my experience, I feel like usually you're kind of it's kind of expected that you're able to solve problems quickly, or that you will maybe do it later or whatever, but they really paid attention here to intentionally wait until people are able to absorb the next step to take the next step, which I think is also a good idea, because then everybody is on board and is able to understand, and you're able to much better continue as a team. Then in the concluding remarks of the introduction, they mentioned that they see one overriding consideration that stands out above all the others was attention to detail, and they further emphasize it here by saying painstaking attention to detail coupled with a dedication to get the job done well by all people at all levels on every element. Success of what must have been one of the greatest engineering achievements of all time, man's first landing on the moon. Of course, you see here they're very proud of it, but this is still something that holds true today. At least in my experience, attention to detail is very important in today's software development. And also the dedication to get the job done well makes for even better software. It kind of takes software from good to be really excellent or awesome. Yeah, I think it's really cool that they mentioned this here and that they noticed this thing, which is not something that you can take for granted. And also, you don't have to take my word for it. Here, an excerpt from the ISTQB Certified Tester Foundation level syllabus. You can see that attention to detail is something that is mentioned as some of the generic skills that is required for testing. So you can see this still applies to today, and they even mentioned it in the same way here as one of the skills that you need for testing. I think that's still, that's really cool to see that this applies like that even 54 years later. So then in the chapter that says testing to ensure mission success, they mention theoretically one no longer needs to test hardware or software after developing a new concept. When I read this at first, I was a bit confused. I didn't really understand what they meant with that, but if we read on, they mention, unfortunately, designs are not perfect. Materials and processes often not work as the designers expect. Techniques alter design. There are room for mistakes, and the engineering and component tests do not necessarily provide all the required data. And they mentioned that, of course, there is sometimes substandard workmanship and human error. And after I read this, I kind of started understanding that here they meant, in theory, if we would be able to develop software without making any mistakes and everything, then we don't really need to test the software. But unfortunately, as in reality, this is not the case. We do need to do this. And substandard workmanship is also something that I experience regularly, where, for example, libraries that are either online or supplied by other, either teams in the same company, if it's a large company, or also by other suppliers, sometimes have substandard workmanship and a lot of bugs. I didn't really pay attention to take care of like edge cases and things like this. And of course, human error is something we experience a lot of times even today. And then they mention that experience has shown that only a well-balanced test program can instill confidence in the delivered hardware and software for a space vehicle. I really like that they already used the word confidence in delivered hardware and software here, because this is still a term that we use pretty much exactly as is today. And they say that a well-balanced test program, this is also something that is still relevant today. Your test plan should be well-balanced to ensure that you don't test too much or not enough, of course. And, this can really give you confidence in your software and make sure that you can deliver it with confidence. And then they mentioned that after the spacecraft fire that they had, NASA launched an extensive review of the Apollo acceptance test practices, which I found really cool to read. I didn't expect when a fire like this happened that this would be the action that they would think about to follow, but that's what they did. And what I found especially interesting was to hear that subcontractors and vendors, they received 79 detailed questions concerning their individual acceptance test plans and objectives. I don't think this is something that is being done today. At least if today something bad would happen, I never heard that, or at least never experienced that. You would get detailed questions where you would be questioned on your questioned on your testing. Maybe you would be questioned on not having skilled enough workers. That's at least what I experienced, but never that it was, considering the tests if they were done well or not. And what I also found interesting to read was they mentioned the survey revealed the inadequacy of environmental acceptance tests, or in many cases, the non-existence of acceptance tests. Maybe many of you will probably be laughing now because this is something that still holds true today, unfortunately. Very often, I noticed a lot of companies have an inadequacy of acceptance tests, or maybe none at all. So unfortunately, this still holds true today, even though I would like this to be something that we should change for sure. And then they mention, in retrospect, several recommendations and points of interest stand out from the test experience that they gained during the 3 different missions over the past 10 years. So here you see maybe it's starting to get interesting, because here they mention things that really stood out to them in the past 10 years. So if you consider the past 10 years, back then was 64 to 54 years ago for us. And I was really curious to see what recommendations and points stood out to them. And these are not all, because there are quite a lot of them, but I picked out some that are interesting or relevant today, I would say. So if we look at the first one, it says, design and development testing plays an important part in the overall test plan. Perform it as early as possible, document the results well, and hold the data for future reference. The perform it as early as possible is definitely something that I feel like is coming back more and more. It used to be a problem, I feel like, a few years ago, where a lot of times the testing was being done a lot too late. Now I feel like it's getting better, but still I feel like we have a bit to learn from the things that they even did right 54 years ago. And they really say perform it as early as possible. And this is something I also recommend nowadays, to do it like this. And I also found it interesting that they say design and development testing plays an important part. So they mention both parts that belong together and that work together as one. That also is something we should strive today, which we are also getting better at, I feel like, but still have some way to go. And they mentioned documenting the results well, and everybody of you that does anything in testing knows that how important it is to document everything and to hold the data for future reference. What I found interesting was pay a particular attention to what seem minor details. And this is something that is something I noticed that makes a good tester as well, that those are people that pay attention to minor details. Nowadays, I sometimes feel, especially when the time is tight, that sometimes when you have a minor bug, it doesn't even get reported, because you think, oh, it's way too much time. But of course, it makes sense to report those things as soon as you find them. And I think we should also get back to doing this even more and pay more attention to that. And also considering performing it as early as possible. To go back to the CTFL syllabus, in the testing principles, the third one is that early testing saves time and money. And they mentioned that defects that are removed early in the process will not cause subsequent defects in derived work products. And so you can see the advice that held true 54 years ago is still relevant today. It's still a good idea to perform testing as early as possible. It's even one of the testing principles. And then they mentioned that tests were rigorous and complete, yet realistic, which I also found quite an interesting perspective on this. They mentioned that it qualify equipment to the designer's desires rather than to the actual requirements. And this is also something that happens sometimes, where tests are a bit over-engineered, where sometimes the tests are being too thorough in certain cases, and maybe not thorough enough in other cases. But I mean, this happens rarely, but at least still, I think this is something to keep in mind. So if you have the problem where you have always that you test something that never really gets applied in real life, this is something you need to take care of. Of course, I can see the tendencies back then, especially with the space mission and being so much in the beginning of software development and hardware development. how they tended to over-engineer things just to make sure that it really works. Nowadays, I feel like we are trying to get away with more and more just, trying to take shortcuts, which is maybe why this is not as relevant today, but still, I feel like it's good to keep in mind. Then one of them is to carefully document, track, explain, and take necessary corrective action on test failures encountered on all production hardware. This is in a similar vein than something we have read before. Remember to really document everything and document what kind of actions you took when there were failures of tests. And what I really found nice was reading, they say even no matter how insignificant or unrelated the failure may seem at the time, experience has shown that major failures always receive adequate attention, which is definitely also still true today. And they say the minor unreported failure is the one that slips by and shows up late in the vehicle test cycle or worst of all in flight. And this is also true today. I experienced a lot of cases where bugs that were minor just slipped by and were deployed to production and then required hot fixes, for example, which nobody really wants to have. So yeah, this is really something we need to pay attention to. Then they say always retest after changes to the hardware or software have been made, set up rigorous controls to assure it. I think this is also still good advice today. I feel like, especially if you have a lot of automated tests, this is something that is being done quite well. The rigorous controls, for example, that they mentioned here could look like if you have a lot of automated tests by simply setting up a CI pipeline where you run the tests in every build. But if you have a lot of manual tests, this is, of course, a lot more difficult. But still, I feel like at least what is really done well today is that at least I've rarely experienced that you are deploying something to production that if there were a lot of manual tests, that the manual tests were not run before you deploy it. And there are maybe even only minor things. But still, it would be nice if we could really make sure that even if once you fix things, that they are still working. So this is still something we should strive for, I feel like, even if it's difficult, especially with manual test cases. And then they say that when possible, test all functions and paths on the installed systems at least once prior to delivery. This comes kind of back to test coverage again. They mentioned here even the word path. So this is something that definitely makes sense, because I experienced a lot of times where you tested something and then thought, well, this will probably not have any effects on it. And then suddenly you deploy it and then suddenly you get some issues with exactly this thing that you didn't test. So it definitely still makes sense today. And they also mentioned they should not simply prove the adequacy of a given component or simple system. This kind of enforces the point from before. And I feel like, yeah, it's definitely true. You cannot be sure that, just a given component or one system is enough if you test it in isolation without testing it in context of the entire system. Then they mentioned that they corrected or removed before the launch approximately 65 potential spacecraft, pilot safety, or mission-critical hardware failures per flight. I found this interesting to see because this kind of proves, they mentioned that by doing those acceptance tests and so on, they were able to remove that many hardware failures, which is a nice thing. And that they also tracked this number, which I think is interesting today. And they also mentioned that some faults remained, which is of course still true today. Testing doesn't have the goal, or it's impossible to get rid of all defects. There will always be some defects. It's just about reducing the likelihood. So I feel like they also got that quite right. And they mentioned that each of the first 10 vehicles flown, they experienced 8 hardware failures. But they also mentioned that fewer than 2 failures per vehicle stemmed from workmanship and quality. They mentioned a bit earlier that workmanship and quality are two things that are one of the things that you can prevent with testing the most. So you can see that this means that, let's say, only a few of those things were things that you could have prevented by doing more testing. And they even mentioned later, better or more thorough acceptance testing could conceivably have revealed only 5. So we see that at least, they say approximately 8 failures. So at least 5 out of 8, could have been, improved by doing acceptance testing, but still this would leave you with 3 or more hardware failures. So this kind of shows how you cannot get rid of all defects. And then they mentioned that no evidence in the flight failure history indicates a failure caused by too much testing. I have to say this is kind of a good point. I haven't experienced a case like this either. I mean, as much as I'm trying to be resourceful and I feel like you should try to not test too much, but still, if you're not sure, it's always better to test more than less because, as they also mentioned here, there's no evidence that testing too much led to, more defects. And then they mentioned that the real effectiveness of the test program came out in the results of the hardware failures. And they mentioned that none of the flight failures affected pilot safety or mission success. So this to me proves that they set their priorities right. They did the testing well because this is kind of the most important part to them, or this was kind of the goal to them. They wanted to not have any of the flight failures affect the safety of the pilots or the success of the mission. Of course, first looking at the safety of the pilots and then the success of the mission. But it's nice to see that they prioritized the testing in the right way that made it possible to have none of those that affected those two things. So they really reached their goal well. I think that's something we can also really take an inspiration from today. We should try to aim more to try to fulfill our testing goals specifically. I feel like, at least in my experience, this is something that we could do better on, I would say. And then what I found quite interesting was there was a mission development timeline. It's quite small, but I hope you can read it. And I'm not sure how much they stuck to this timeline in the end, but you can see that the testing and training phase that they kind of put in here was only 3 to 4 months, and this includes both testing and training. But you can also see that the software development was done in around 3 or 4 months, and also the unit and subsystem tests and the system tests were done in 3 to 4 months, which is very impressive to me. I'm not sure if they really were able to do that, especially if you think back to the numbers I've showed you earlier with the 513 days, work days of testing. If you need to cram that in 3 to 4 months, that's quite a lot of work and quite a lot of people that worked on this. And I think it's really commendable to see that they were able to pull something like this off, even though they weren't as advanced as we are back then. And it wasn't as easy for them to work on things in parallel as it is for us today. So I think this is really impressive if they managed to do this in this timeline. And then for the last point, and under the chapter Action on Mission Evaluation and Flight Anomalies, they mentioned that system anomalies caused by design deficiencies can generally be traced to insufficient design criteria. Consequently, the deficiency can pass development and qualification testing without being detected, but will appear during flight under the actual operating environment. I feel like this is also something that is very true today, that sometimes if you're not doing the requirements right, then you can do all of the development and testing you want. It will not be detected, but it will actually appear once you, like here, during the flight or when you're running the software, when you're operating it actually. And I feel like that's something we should be very careful about, because of course, if the requirements are done incorrectly, then this is something you can't really easily detect afterwards. So I think it's very important that we always try to understand the business case and try to really question things if we feel like they don't make sense from a requirement standpoint. I feel like not enough work is being done on trying to question requirements at the moment. They are kind of accepted as being, as they are given. But I feel like this is the first step in the process, and I feel like this is the step where we could have a big impact as well and could do more on as well. So I hope this was interesting to you, and thanks a lot for listening. Is there any question?